So setting out a problem to find the volume and surface area of a solid, which is what you're going to be doing in the assignment, assignment 2, or part of assignment 2. Let's have a look at the question, and you'll see it. Determine the mass of a hemispherical copper container, let's make it a bit bigger, whose external and internal radii are 12 and 10 centimetres, assuming that 1 cubic centimetre of copper weighs 8.9 grams. So, plan. What are we going to do? Let's not look at the problem and go through it now, so don't tell me what to do exactly, but what's the sort of idea? What have we got to do to solve this problem? Ideas. If in doubt, the first thing I would do would be to draw it. So I'm going to try and draw it in 3 dimensions. It might not work. There's the top of this. Yeah, that's not bad, is it? Okay. So it's a hemispherical copper container. So that means it's got a thickness. So that's the sort of top of the thing here. So what have we got to do to try and find, what are we after? The mass. So we've got to find the mass. Find the centre point. With what aim? I told the radius. All right. So yeah. So with what aim? What's the plan for that? Right. So in other words, we're trying to find the area of the top. Yeah. So we can then get. Okay. Yeah. You had your hand up at the back. One cubic centimetre would weigh, did you say? Well, we know that 1 cubic centimetre of copper weighs 8.9 grams. So yeah, if we could find what the volume of this thing is, then we just times that by 8.9, we got the mass, haven't we? So the mass is going to be equals 8.9, which is actually the density, isn't it? 8.9 grams per cubic centimetre. So actually what they're telling you there is the density of copper. 8.9 multiplied by the volume. So you've got to find the volume of this thing. So that's what I was wondering whether or not you were trying to tell me. A plan of how to find the volume. What we're going to do to find the volume of this thing? Right, yeah, so we want to find the volume of the outside of the, or if you like, the whole thing, yeah. Assuming there was no dip in it. Is that making sense? Yeah, the volume of the whole thing. And take away the volume of the center of the hole. I could maybe have written that better, but does everybody see what I'm saying there? Can you visualize this thing, some sort of copper container, which is hemispherical, and it's got a hole in it? Formula to find the volume of a hemisphere, then. Let's look back at our things. Which one's going to help us? No, not the cylinder. The sphere here. It's a hemisphere cut in half, so that's what we're after. So what's the formula for the volume of a sphere? 4/3 pi r cubed. So what do we do with that? Right, so where are we? So the volume of a sphere is 4/3 pi r cubed. So therefore, volume of hemisphere is a half of 4/3 pi r cubed. So 4/3 pi r cubed over 2, which actually turns out to be 4/6 of pi r cubed. But we could leave it like that so that it makes sense. So what have I done so far? I've drawn it. I've written down what I'm going to do. I've sort of thought of my plan. If I was trying to present this as a report, somebody's asked me, I've got this container, I've got to find the mass of this thing, I would probably do exactly this. I'd draw it, and then I would write down what I'm going to do. I'm going to find the volume of the whole thing and take away the volume of the whole. That's my plan. And then what's the formula that's going to be used here? Volume of the sphere, and therefore the volume of the hemisphere is half of that. Now what am I going to do? Now what am I going to do? There's the question. What answer? Yeah, so we're now actually going to do it, aren't we? Yeah. So to find the volume of the sphere, what we're going to do? Here's our plan. We know now got the formula. So what do we do? Yeah. Yeah, I've got, so which radius are we going to use first? The external one, which is 12, find the volume of that, and then use the internal radius, 10, find the volume of that. Agreed? And then take one away from the other. Do you want to do that for me? So the next stage, find volume of outer sphere, if you like, rather than the whole thing. Outer hemisphere. And then you do your calculation, and then volume of inner hemisphere. Do your calculation. Okay, so if we work out the volume of the outer hemisphere, we get, using the calculator, we can do it in one hit. 3619 cubic centimeters for the outer volume, 2094 for the inner volume. So now back to our plan. We've got to find the outer volume, or the volume of the whole thing, and take away the volume of the whole. So in other words, the volume of the container equals V outer minus V inner. So that equals 3619 minus 2094, which is 1524. Is it? 1524 cubic centimeters to 4 significant figures. So now we've got the volume in cubic centimeters, we've just got to multiply that by 8 by 9. Is it? Okay. Yeah. Head's always better than a calculator. So therefore, the mass equals 8.9 times 1525, and we get hopefully the answer in the textbook. If I've just to finish this one off, note the volume of a sphere, so the volume equals 4/3 pi r cubed over 2. That's our formula. It's the same formula for both calculations. It's just that we had two different figures in. So actually, the volume, the total volume equals 4/3 pi r outer cubed minus r inner cubed over 2. I could have done it in one hit on the calculator like that, because V out minus V in equals 4/3 pi r out cubed over 2 minus 4/3 pi r inner cubed over 2. Whoops. So if you look at it, we've got two terms in this expression. 1, 2. We can factorize. You remember what factorizing is? take outside a bracket what's common to both. And if you look at it, the 4/3 pi over 2 is common to both. So I can take 4/3 pi over 2 outside the bracket, leaving just the r out cubed minus the r in cubed. So mathematically, if you were comfortable with the algebra and all that, you could get to here, and then you've got a general formula for any shape, anything like this with different radii. You just plug the numbers in to this, okay, and you've got the solution straight off. Okay, so first step, draw it, visualize what that shape looks like. It's a cone on top of a hemisphere. So if I draw just a side view, I'm not even going to attempt to draw this in 3 dimensions. We've got a cone on top of a hemisphere, so it looks a little bit like that. If I look at top view, so from there I'm going to see a circle with the top of the cone there, okay? So that's sort of what it looks like. We've got some information. We know the diameter of the hemisphere and the cone are each 4 centimetres. So the diameter is 4 centimetres. So that's this dimension here. And we know the total length of this bob is 5 centimetres. So from here to here is 5 centimetres. So we could draw it and put on the information as far as we know it. Plan to find this volume. Yeah, but how are we going to find the volume of the whole thing? Yeah. Okay, so we want the volume of the hemisphere, so we find a volume of the whole bottom of the sphere and half it, yeah? And then what? Find the volume of the cone and then add them together, yeah. So we're going to find the volume of the cone. Volume of cone and volume of hemisphere and add them to get the total volume, aren't we? That's our plan, okay? Formula for the volume of a hemisphere. Can anybody remember it? Hemisphere, let's call it HS for hemisphere, is volume of the sphere. Yep, so over 2. And for the cone? Okay. Yeah, that's good. So you either look them up or you know them, that's fine. So we've same procedure that we've drawn it, got our plan, we've found the relevant formula, the volume for a hemisphere and the volume for a cone. Now, so let's find the volume of the hemisphere. Equals 4/3 pi times, what's the radius? 4 centimetres over 2, which equals. So we can work that out, okay, and give it to an appropriate accuracy. What about the volume of the cone? Pi at 1/3 pi times the radius squared times the height. The radius is 4. Same, isn't it? But what about the height? What about the height? No, it's not, is it? We know the whole thing is 5. We want this distance from here to here. So can we have everybody looking at this for a second? And you can perhaps tell me the answer. Oh, made a mistake, by the way, didn't we? The diameter's 4. So when we come to the volume of the hemisphere, that should have been a 2, shouldn't it? So actually, when we get to here, maybe I should have written down that the radius is 2 centimeters, which is half the diameter, because the diameter is 4. So here I could have again written that the radius is 2 centimeters, but the height equals, well, we're not sure what the height is. Let's think about this. What will it be? Because, yeah, if we look at this, we've got a little bit of an extra thought to put into this, because from here to here is the radius, and that's 2. So if that's 2 centimeters, then this distance from here to here must be 3 centimeters. So in other words, we've got an extra little calculation to do to get that height. So now we can say that the height is 3 centimeters, and then we can finish the problem. So the radius is not 4 at all, the radius is 2. So that should be a 2. And then we can go ahead and carry on and finish the problem. I don't want to finish that off, because you can finish it afterwards and check you get the answer in the text. Any questions about that, though? The procedure. What about, I want to add an extra dimension to this question. It doesn't ask you to do this in the textbook, but I want us to find the surface area of this plumb bob. So we're designing these things, we're making them, manufacturing them, we want to spray them afterwards to make them look nice, spray them gold or something, okay? So we want the surface area, so we know how much paint to buy. How are we going to go about doing that? What's the plan? Plan to find surface area. Let's redraw our plumb bob, so we've got it to refer to. I'm tempted to put 2 dots and a smiley face on there. You've already done that, have you? So, what are we going to do? Yeah. Yeah. Okay. Or don't include in the first place. Yeah. Daniel, did you hear that? Yeah. No? Right, okay. So how are we going to find the surface area of this thing? We're going to find the surface area of the sphere and half it. And then we're going to find the surface area of curved side of cone and add them. Right, what's the formula? If you look back in your if you look in your textbook, I'll put it here. What's the formula for the surface area of the cone, of the hemisphere rather? That's the volume, surface area, 4 pi r squared. So we want 4 pi r squared, but we want half that, so what will it be? 2 pi r squared. So surface area for the hemisphere is 2 pi r squared. Do we know r? Yes, r is 2. So that's okay. Look back at our formula. We want the formula for the curved surface area of the cone. Where's the formula for the surface area of a cone? Yep. Here it is. Yep. Do we want all of that formula though? And this is the key part of this. No, we don't want the, right, we don't want the base of this cone because it's attached to the hemisphere. So we only want the curved side of the cone rather, which is the first bit, pi RL. Yep, that's important. So this is an example of where we don't use the whole formula. So going back again, we could then say, okay, the surface area of the cone is pi RL. But what is L? But which length? L is, in fact, if you look at the formula, this length. So how are we going to find that? Pythagoras, yeah. No, it's not 3. This distance is 3. We want this distance from here to here. This is L. So it's a right angle triangle, Daniel. Can you put that down a second? Focus here. Right angle triangle. So there's the right angle. So we've got that length there, which is 3. We want this distance from here to here. What is that? It's the radius, isn't it, which is 2. So we've got 2, 3. So we can find that using Pythagoras. Okay? So to find L, use Pythagoras. Again, I'd write this down, what I'm going to do. So when I'm reading it later, or you're giving it into me, I can read it. This is what you're doing. I'd even draw it. We've got the height, and we want this distance here. We want L. That's 3. This is 2. So what would I do to find L? Yep. Yep. Equals L squared. Yeah, that's Pythagoras, exactly. So we work out what that is. 3 squared is 9, 2 squared is 4, 9 plus 4 is 13. So what do I do to get L? Square root. Not square root it, not half it. Square root of 13, whatever that is. That will give me L, and that's the L that goes into that formula to find the surface area of the cone. And then I'd add them together.